to be here. Hello.
Hello, sir.
Hello, sir.
Hi. So, so as I told you, so today we will be kind of doing this algorithm that I kind of promised you guys. About the learning algorithm. So this is kind of a example of a greedy algorithm that we will be seeing. Before I start, did you guys manage to think about that problem a little bit that we discussed yesterday?
Yes, sir.
So, did you make any progress?
Sir, I thought of a couple of things, but actually, since we've done a bit of the solution in the parametric inference class, so actually we've seen a bit of the approach.
You've seen a bit of the approach where? Hello. Am I audible?
Yes, sir.
Yes, sir. We got disconnected for a second there.
So I got disconnected?
No, sir, I got disconnected.
Oh, okay.
Yeah. So I was saying we've seen an approach to this problem in terms of logistic regression and parametric inference.
Okay.
But if we were to discount that and think about it in a fresh way, I was thinking about something like maybe just adding the vectors which have a plus classification and subtracting the minus classification, what we can do from there. So I wouldn't call it progress, but still thinking about the problem.
Okay, good. No, that's a good way of start actually. Okay.
So I was also thinking about the problem. So I was thinking in terms of the rotating needle thing that I was pointing last time. So if our objective is to go to theta step, right? And then we begin with some, let's say theta1, theta0 initial.
Right.
So that is going to create a partition. Let us say we start with some value of theta1. It is going to classify wrongly, rightly, but it is going to give us some.
Right. It is going to give us a hyperplane. Yeah.
So basically, I am basically thinking in 2 dimensions because, of course, it is not a 2-dimensional thing, but it helps to think in like Rn is like a 2-dimensional picture and pluses and minuses. So we have a certain orientation, and we want to reach a orientation where all pluses are on one side and all minuses are on one side, right?
Right.
So let us say we have a theta1, and we look at, let's say, one side, okay, and that side. So we look, first of all, want the positive side to have all the pluses, right? So let's say on the positive side there are some negatives, right? So we want to move it to the other side. So I was thinking
kind of move it, in some other direction, right,
to the other side, right? So what I do is, this theta1 has a positive side and a negative side, right? It has a positive side. So what I do is, on the positive side, the negative point, which is at the smallest angle, I cover that. Like I rotate my needle. What I do is, like, I
rotate the needle just to take care of that one.
Just to take care of the point which is closest. So what I'm trying to do is I'm trying to shift it a little bit, the smallest angle bit, to cover like one irregularity.
Right.
I'm not sure it has solved the problem, but I'm trying to displace it as little as possible, but improving my solution, trying to improve my solution. But what I was thinking, so this is what I was thinking. I was not able to convince myself that when I'm rotating it, then I'm also, like, if I'm covering this point also, I'm exposing the other half also.
So this particular idea or intuition that you have is very good, and in fact this works perfectly for the 2-dimensional setting. Okay.
But sir, I was not able to prove anything formally.
I think in 2-dimensional setting you will be able to prove that your algorithm will give you the correct answer, and it's very fast. Okay, but the problem is that in a higher dimensional setting, that is not going to be the case. Okay.
Sir, in the higher dimensional case, is the problem about the time complexity or the correctness of the algorithm?
No, correctness itself.
Okay.
It's not very clear. There are many ways you can shift it. In 2 dimension, if you just want to take one point to the other side.
Yes, sir, that is the advantage. That is why I was doing it in 2 dimensions. There's only one plane of rotation.
There's only one plane of rotation, and so you know exactly how much you have to kind of.
So we can, like, we have something like
smallest angle. That is not the case.
Smallest angle to rotate and which direction to rotate, like clockwise.
Yes, in higher dimension, I guess we can. Suppose for 3 dimension, we can make a plane and just rotate the. So am I audible?
Yeah, you're audible. Go ahead.
So the irregular point, we can just do a projection on the initial plane, and using that projection, we try to go through that direction, like rotate through the direction.
Okay, I mean that's one thing. Good. So I think many of you have. So you are giving us some ideas, right? And I'm not telling you which idea is going to work or not. Okay, I myself don't know. And so there is, all of them have 2 problems, right? Number 1 problem is that, is your algorithm actually be correct? So for example, in this, what you just now told, Anurag, right? That you shift it in some way, okay? You optimize it in some direction, some way you shift. It is not very clear whether some point which was classified properly suddenly gets misclassified.
So there might be a thing like it is it's the algorithm might go into periodic motions or something.
Yeah,
We
so
cannot-
exactly. So if it kind of you take a point which is misclassified, you change the angle, change the vector accordingly, or change the hyperplane accordingly to take care of that point. Okay, but then maybe some other point that was properly classified has got again misclassified, and you might go into circles, right? The question is that does this algorithm actually stop itself? Okay, and secondly, if it does stop, what is the time complexity? After how many steps does it stop? Okay, so I will be going to give you another such algorithm which is exactly similar to what you guys are saying. Okay, exactly. It starts with a hyperplane, some hyperplane, doesn't matter what. That hyperplane gives you some positives and negatives, right? Now, what you will say is that, okay, some of the points are misclassified. What does misclassified meaning? Meaning it should be if a point which is a positive is actually in the wrong side of the hyperplane, where it should not be. That's a misclassified point. Or a point marked negative is in the other half. Right? So in that case, we will take one such point, any one such point, arbitrarily. You give me one point, says that, okay, this hyperplane is not right because this is a witness of that. You are misclassifying it. And I will be changing the hyperplane. Oh God. Hello?
Yes, so for like 5 seconds you were inaudible, but you are audible. Yes.
Oh, okay. So whatever I told you was it audible? I was describing the algorithm to some level.
Yes, sir. It was audible.
Okay. Okay. I suddenly got this message that. Okay. Yeah. So okay. So yeah. So as soon as I find one point which is misclassified, I want to change the hyperplane in a particular way. Okay. And that's it. Okay. I keep on doing it till the algorithm. I mean, keep on doing it. Basically, that's it. Okay. So let me actually.
Sir, how you are choosing the point, sir?
However, it doesn't matter. Any
Okay.
point which any
misclassified point.
Any misclassified point arbitrarily.
Okay, sir.
Okay. So let me give you the kind of a presentation maybe that will be kind of help you to do this. Sorry, this is not the one. You see this? You see your?
Yes, sir.
Which one are you seeing?
The perceptron learning
algorithm, right? Okay, so okay, good. So let me quickly go over this thing just to kind of ensure that everybody is with me. So you have a set of data points. So and the data points are of the form x1, y1, x2, y2, and so on. But the xi's are basically points in the d-dimensional plane, and the yi's are the labels. It is either +1s or -1s. Okay, so you can think of them as labels. So yi's are the label of xi. And what we want is a linear classifier. So what is a linear classifier? Meaning it's a vector theta, as we pointed out last time. A vector is same as talking about a hyperplane, right? I mean, we can talk about the perpendicular plane, which is of the vector, which that is the hyperplane. And the idea is that it should be such that if you take the dot product of theta with x, or I mean with xi, say, right? Then it will be either some value will come out, either positive or negative. The sign of that must be same as y. Right? Everybody with me?
Yes, sir.
Yeah, I mean, this is, please try to answer something because I'm now, I think my network is a bit shaky today. Okay. So once you have this source, okay, so again, this is something that we have done in some since last class. I'm not going to go into it. that this is used a lot in machine learning. Okay. So we have this lot of this data, then you want to identify them. And pictorially, in some sense, you are given a set of points. Some of them are, say, reds and some of them are blues, right? And of course, and the idea is that they can be separated by a hyperplane. Now, find that hyperplane. Okay. So of course, there is an issue that if I have, say, if a lot of points are right at the border, right, all the red points are right at the border along the line, and the blue points are right at the border along this point. So then things can become a bit more tighter. In some sense, if the collection of red points or collection of positive points and collection of negative points are somewhat separated by some amount, then my life should become easier. Right? That's a kind of natural thing, that if these 2 points that I am to separate, they are far apart in some sense in geometry, then must be easier for me to solve it. Right. Good. Now, here is this algorithm. This is an algorithm for 1968 by these two famous biologists or neuroscientists. They're called Minsky and Peppard. And it's like I mean, you can think of this is the first machine learning algorithm that was ever produced to some level. See. Now the algorithm is just this much. Okay. Let's see, what is it? You start with some theta, okay? You can start with some random theta, doesn't matter what is it, okay? Now, while there exists some t which is misclassified, okay, so sorry, I mean, I have lots of mistakes are here, such that say yt is not equal to sine of theta dot xt, okay, this would be t. So this is a misclassified point. What do I do? So I will update the theta, okay, and I mean choose any such point, doesn't matter, xt, yt, and how do you update it? You update it by adding, okay, this. So xi is a vector, right? Or xt is a vector. You add xt to theta, but you have to multiply xt with the yi. That's it. Okay. Now in the two-dimensional setting, you can actually see what is going on here. Okay. So I mean, at least to say it that this one, I mean, so if I have a hyperplane, okay, and if I find a point which is a positive point, which is
sir, what is happening here, sir, in the updating stage? Theta, yi is plus minus 1, right?
Y is plus minus 1, right?
And xi is a RD vector, right? And theta
X is
also
a RD vector. Yeah. So it's like I'm just adding or subtracting, whatever you want to say. Okay. If yi is,
what's the point of doing this? Even in two dimensions. Even in two dimension.
Okay. What's the point of doing it? Maybe I should connect my iPad. So say in a two-dimension setting, what is going on, right? So you have a point. You have a oh God. My connector or what? Just one thing, give me 1 minute, okay? Just give me 1 minute. Hello. So it seems that I have lost my connector to the iPad. Let me do one thing. Let me try to join it from another account. Just 1 second. Just give me just 1 second. That's okay. Hello, can you hear me?
Yes, sir.
Okay, so just 1 second. So can you see that I have another account that is there?
Yes, sir. Yes.
Yeah, so I'll be. Do you see my, yeah, you can see my screen, right?
Yes, sir.
Okay, unfortunately, we have to kind of go back and forth between some of this stuff. But let's see, okay? So here in the two-dimensional setting, right? What happens? I have a two-dimensional setting.
Sir, I guess you can write on the slides.
Yeah, but I can write only in my iPad, not on my computer. I'm teaching from my computer.
Okay, sir.
So I have said these various plus points, right? Yeah, so something like that. And I have these minuses. Make it with different color. Right. Now, okay, what is my vector? The vector that I have is say something like this. Say this is my vector over here. Right? So the hyperplane is say like this. Correct?
Yes, sir.
Yeah. So here now, what should I do? Naturally, the thing to do is I should be moving it in this direction.
Yes, sir.
Right. But what I do is that, okay, so I'm finding this point here. So I find some point, okay? I say let this point be the point that I have found out to be a mistake, right? So this point, what should I do? I should add this point, because if I add this point, right? So this point is basically here. If I add this point, it would move in, this one will move in this direction. I mean, at least it is in the right direction where we are hoping to take care of this particular misclassification.
That is what I wanted to ask also, because this operation theta is equal to theta plus ytxt does not guarantee that this point is now changed.
No, of course not. It doesn't guarantee that. I am not saying that, but at least it's moving in the right direction.
Yes, it will move in the right direction.
Okay.
And so,
yeah, so theta equals to, yeah, tell me.
Yes, sir. As we add, so the size of theta increases and the rotation to this thing would be decreasing. So eventually,
that is one. Okay, I mean that's okay. So we will come to that. But so as somebody pointed out, it's not clear that this first step will take care of this. Okay, but at least it will move in the right direction. That's all.
Yes, it will move towards the point, sir. Yes, sir. It will move towards.
But what happens if the point that I'm looking at is, say, this point. This is also misclassification, right? In that case, what should I do?
So you want to move the vector away from this point because it has to be classified on the other direction.
I want to move the vector away from this point, right?
Right.
And because I want to kind of, so in that case, I should not add this point, but subtract this point.
Right.
Subtract this vector, right?
Right.
And that is why this white is there.
Yes, sir, that white is clear.
Okay. So at least in 2 dimension, you should be able to convince yourself that every move, this expression that is there, at least in the 2 dimension setting, even in higher dimension setting also, that the vector is moving in the right direction. By how much, that's a different issue altogether.
So the right direction, not in terms of the absolute linear separator, but at least in terms of
take care of that point.
Of the specific point, right? Right.
To take care of that specific point, okay?
Right.
That's all that we are saying. Okay. Again, I think this is a greedy algorithm.
Right.
In some sense, it is just like greedily trying to find out something and then trying to produce, trying to rectify it.
Right.
Yes, sir. We can imagine, like, if let's say this plus was the only point in the vicinity which was wrong, and everything was well separated, then this line would keep moving towards it till it would correct it. Right?
Exactly.
Yes.
Okay. Now, what is a big problem is that it can also move it. See, if this point, okay. So if this plus that was misclassified is much more further away, right? That's a possibility, right?
Right.
When just the distance or the length of the vector is huge, I mean, length of this point is huge, then this moves by a huge amount.
Right. There has to be some normalization with respect to the length
No,
of
we are not doing any
the current
normalization
theta.
at this point.
Right.
Okay.
Okay.
So it is possible that something, so it moves in such a way that there was a some class which is very close by here, which was kind of correctly classified, but they suddenly, after moving it, it might become something like this, and something that was previously classified properly becomes unclassified properly or misclassified.
Right.
Right. So that is also that's a big problem. So it's not like a very increasing thing, like, okay, let's first classify this one, then classify this one, then classify that one. No. Right?
There's no monovariant that we can rely on to give us a proof of completeness.
So there's no reason why you can say that, okay, if something has been already been looked into once, it will not have to be looked into again.
Right.
Okay. So this algorithm, under no stretch of imagination, looks like a algorithm that will obviously stop. Right?
Yes.
But somehow this algorithm was what was proposed and was used by in the research world, in the research world meaning in this experimental world, left and right, for nearly, I mean, it is still used basically, but it was used without any reason to believe why it doesn't work. It was used in this medical world and all for 20-30 years without having any proof of it. It was for 10 years. It took 10 years. Okay.
So it was used for the general n-dimensional case as well, not just 2 dimensions.
General random d-dimensional setting.
Okay. Okay.
Okay. It was proof for general random d-dimensional setting, and surprisingly enough, this algorithm was giving the right answer. So,
right.
So this was giving the right answer, and it was still stopping. Every time it was stopping, it was not like going into an infinite loop kind of stuff that never stops. So this whole algorithm at some point of time was halting and giving you the right answer. Now, see, this is a problem that we face in real life applications a lot, because many times what happens is that, I mean, maybe an algorithm is working, just because the real life instances for which we are running it, they have some special property.
Right. Yes.
Okay, so while this algorithm is not correct as such, this algorithm might be just working because we are applying it on real life instances which are have some nice properties. Okay, and then it will just take someday or other someone whatever use it on something and they will misclassify things and it would be a disaster. It can happen. So this we call as heuristic algorithms. Okay, an algorithm which seems neat, simple, and what is the proof of correctness? No, nothing. You just do it, and it seems to work. Okay. So let me stop my screen share. Okay. So
the motivation is quite clear behind it, but it's still whether it will achieve exactly what we need is not clear. So
exactly. Yeah. So the algorithm is very clear. Okay. Right. But still, why it happens is unclear. Okay. So it's not very clear why the algorithm stops. And more importantly, if it stops, is it like some kind of a crazy amount of running time or not? Okay. Amazing thing is that it was proved in this 80s. So 68 was the algorithm, it was proved in the 80s. So actually, I mean, less than 20 years, but not too much less. Okay. So here is the other thing. So see, there's a best classifier, right? Theta.
Yes, sir. Now, that is definitely required, right? Otherwise, we definitely know it won't stop.
Yes, if there is no best classifier, then of course the initial premise is not. I mean, it is not binarily classifiable. Right. Period. Right. So of course there is a best classifier, and that's what we are trying to kind of reach to kind of stuff. And say that this best classifier has what I told you in the beginning, that there is this some amount of gap between this red and blue points, right? How are you doing it? You're saying is that if you take this dot product with any of the xi's, okay, of course, all that we are kind of guaranteeing is that this sign of theta dot xi is equals to yi. But I also say this cannot be too small. The theta dot xi must be more than some constant, some number, some parameter, which is gamma.
Sir, this is the absolute value of theta dot xi, because
absolute value should be, sorry.
Okay.
Yeah, right. Absolute value of theta dot xi is more than gamma. Okay, for some gamma. So it kind of says that there is a band. Just take here, it says a kind of, there is a small place of leeway. There's a small band between this red points and blue points.
So there's a best classifier that doesn't actually pass through one of the points.
It doesn't pass through any of the points, or forget the best classifier. The idea is that there exists the set of all red points and set of all blue points is separated by some amount, which is kind of which can be talked about as theta, as gamma. Okay.
Yes.
And we can also assume without loss of generality that all the xi's are norm of that is less than some r.
Right.
Okay, you can think of it that you can some r. In that case, the perceptron algorithm will stop after at most r squared by gamma squared. Okay, so this is the theorem that was finally proved in the 80s. Okay, is the algorithm clear? Is the proof? Is the not proof? Of course, the theorem clear? What we are trying to do?
Yes, sir.
So if I could prove this one, not only it will give you a proof that the algorithm stops, but it will also give you an upper bound on the number of steps up before it stops. Right?
Right.
So let's see how much is. So I'm going to not be presenting it. I will be presenting from a note that is there, and I will in fact put the notes on the web page also. Here. Okay, and it's like almost a kind of a very beautiful thing that is there. Okay. Good. Okay. So the first thing is then look at here. Okay. What happens? So consider the dot product of, so I have this theta that keeps on changing, right? So theta k is basically with the vector. Yeah.
Sir, are you writing somewhere?
Oh, you are not.
We are able to see this slide only. Please
Oh, you're not
share
able to see
that
this, right?
screen.
Oh, sorry,
Yes.
sorry. I think I know what happened. Yeah, can you see the slides now?
Yes, sir.
Yes, sir.
Yeah, I'm not slides. This is like a subset of notes. Okay. So say that this I have this theta that I was changing, right? So say theta star is the best classifier. Okay, and I have this theta that I kept on changing. So say the theta after first round or after first round is theta 1. After I've looked at the second or edited it a little bit, after the I've treated the second what is that called, second second misclassified point, then it is theta 2 and so on, right? So theta k is the vector after the kth round, right? Now what happens if I take the dot product of this vector with theta star, right? So just put it this way simply. The theta k plus 1 is nothing but theta k plus gamma x y t x t. That's by definition, right? I was updating it accordingly.
Yes, sir.
And that dot theta star is theta k dot theta star. I'm just opening up, right? You can see my cursor here, right?
Yes, sir.
Yes, sir.
Yeah. So the first one is whatever was there before. The second one, let's see here. Okay. Now theta star dot xt, right? It was absolute value was more than gamma, and its sign was equal to the sign was equal to yt. So this quantity is more than gamma.
Sure. So actually,
Yeah.
yt xt theta star, this whole thing has to be greater than gamma. And in
Yes.
fact, like we can remove the absolute value and just say yt xt theta has to be greater than gamma for all t.
Yt xt has to be greater than gamma. Sorry, I don't get you.
So I was saying that we can revise that condition that xt times theta star has to be greater than gamma.
Okay, so you are saying that you can change it by saying that yt xt is greater than gamma. Yeah, if you want to say it in that way, that also is fine. Right. They actually both are identically and the equivalent statements.
Right.
Sir, sorry, sir. Could you please repeat what was gamma? I just forgot.
So gamma is every point xt dot the theta star, the absolute value is more than gamma.
Okay.
Okay. But since we know that xt dot theta star has sign equals to yt, so yt times xt dot theta star is nothing but absolute value of xt dot gamma, xt dot theta star, which is more than gamma.
Right.
Sure. So we can just define gamma as the infimum of yt xt theta star, and by our definition, theta star is such that yt xt theta is greater than 0, and since there are finite number of points, so the infimum has to be greater than 0. So gamma has to be something strictly positive.
Right, gamma has to be strictly positive, right? Yeah.
Right.
So now, so that basically means that this theta to the power k plus 1, right? It keeps on growing. So whatever theta that we are basically finding, its dot product with theta star keeps on growing by a gamma after every round. Correct?
Yes.
Or in other words, that theta k plus 1 dot theta star is more than k times gamma.
Right.
I mean, this is like nothing there that we have done. Oh, good. That is one part of it. Okay, so remember this part, this equation 4. And now let's look at it another way. Okay, what is the norm of theta k plus 1, or the distance of or size of theta k plus 1, right?
Yes, sir.
So theta k plus 1 is nothing but theta k plus xt yt.
Right.
Let's look at this norm, right? Norm square. I'm just opening up this whole thing by the definition of the norm.
Right.
Now, whatever this quantity is, let it be, okay? So theta k. Now I have this quantity. Now what is this quantity? Now this quantity I know is, see, yt square is 1, and xt square, if you remember, that we assume that all the xt square, the norm was less than r. So the xt's norm was less than r. So this norm is less than r square. Right? This whole thing is less than r square, the norm square. Right? And the last term, what is last term?
So this is greater than
Something
gamma.
positive.
This is something.
Oh, okay.
This is not positive.
This is negative.
This will be
negative.
negative. Yeah, by
Because we chose t to be such that this is negative.
Oh, okay.
Exactly.
Yeah, so
because
that
t
would-
was such that was not classified by the
Yes,
kth thing, right? By the
Yes, sir,
kth theta.
So this was misclassified. So
This is
that-
misclassified. Right.
Yes.
So this is negative. So that's why you have this equation. Right. So you have something plus r square and a negative term. So this norm basically goes up by at most r square. Okay.
Yes, sir.
So in other words, you can do this whole thing here. So you get this one. The theta k plus 1 whole, the norm square of theta k plus 1 is less than k times r square.
Right.
Right. Again, triviality.
So we have lower and upper bounds to
Now, so what is this one? So theta k plus 1 r square we have is bigger than k square by gamma square times gamma square, because this is bigger than k by k times gamma. Another way, it is less than k times r square. What does it mean? If you just solve this whole thing, you will get that k, the number of times the operation can be done, has to be less than r square by gamma square.
Oh, okay. Right.
Now, I think you should be able to appreciate this proof to some level, okay? And now it's a very simple proof.
Yes, sir.
If you know where to look at it.
The smaller the gamma and the higher the r, the more problem we have.
Yes, the smaller the gamma means there's a smaller band between this positive and negative sign.
And more
and
the
r's
r,
are big.
the swings will be more, so it will start misclassifying.
Yes, so you have to have more and more. But
so we've created a lower and an upper envelope for this function of growth.
Yeah.
And we've shown that they converge at this point, r squared by gamma squared. So
kind of, you can think of, the converge at this point. After this point. That after k is less than, so you have this upper bound and lower bound, and basically this implies that k, you cannot have this whole thing going on. Yeah.
Okay. Right.
So now this is something that is like to me it looks like one of the most beautiful proof of correctness of algorithms. And in fact, it is one of the best proof. The algorithm is a trivial algorithm. Actually, there is an algorithm written here. So this is the whole algorithm that is there. Right?
So in one shot, it actually gives us the complexity as well as the...
Right. And it's one shot gives us one, right? The proof is not at all hard, and yet it is not at all obvious.
Right.
If you know where to look at it, you have it. And that is exactly the reason why people took more than 10 years to find the solution. this proof of this.
So, sir, I was asking, like, the proof actually is very, the way that proof is constructed is very intelligent, but at the same time, it is like, so how did they, they started
come up with this
like,
proof?
Yeah, this line of thought. Okay, let's say we can.
I cannot exactly tell you how they started it, and the reason I cannot tell you is that because it took 10 years for them to come up, right?
So did they start with like, okay, but for that, like a separation for
no,
a smaller
I don't think they thought about it in this way. Okay, so what happens is that, of course, you want to kind of, so this kind of technique is not unknown, okay, where you kind of have a potential thing and you try to say that something is not going for too much time, right? So something is increasing, but it cannot increase for too much time. So, but here what they're saying that, okay, I mean, they do it in two sides, in both upper and lower bound thing, right? And yeah, I mean, I can tell you how I would analyze this proof, but I would be very much, telling a lie if I tell you that this is how people have thought about it. If that was so easy, then they would have come with it before that. It is much easier to say it in the hindsight that, oh, this is how you should have thought about it. Right. I mean, this is true for, like, it's true for all classic proof techniques, right?
Yes, sir. It's like knowledge bias. It's when you know you can't unknow a certain.
Yeah. Or the simple say this Cantor's diagonalization technique. Once you have it, and then wow. I mean, how is it people did not have it for so long?
Right.
So that's kind of a proof here, right? So the reason I wanted to really explain you is this one is that this particular proof or algorithm shows you a few things. First of all, there are these heuristic algorithms which are not bad and they should be respected. They might very well be correct. Just because they have not been proved correct doesn't mean that they are not correct. But it is also our job to keep on working and trying to find out the proof finally. The proof can take time and can be very good, but it can take massive amount of time. So that is one part of it. So this is a place where heuristic algorithms have been coming much beforehand than the. So right now in the world of machine learning, there are many algorithms, including the things like neural networks and all those things that it's very common nowadays. These are algorithms where we don't have any proof of correctness. We have zero proof of correctness. But supposedly it's working. So either we have to kind of check out whether, I'm not saying that all heuristic algorithms are great. In fact, some of the heuristic algorithms have led to some massive disasters, including the recent set of the Boeing planes that kept on crashing. The reason was basically a wrong machine learning algorithm that was being put in.
What are heuristic algorithms?
So heuristic algorithms are algorithms that don't have a proof at this point.
Oh, yeah. Okay.
They seem to work. Okay. They are being run on some data and they seem to work. But there's no proof of correctness. And forget the time complexity. And the proof of correctness is also not there. Sometimes even time complexity also we can talk about it heuristic. So there are some. Also, this also shows another important thing that this is a greedy algorithm. A very simple algorithm which is done in a very greedy way. And this also shows how hard is it to prove correctness of greedy algorithms. Yes. Greedy algorithms are very tricky to analyze. Okay, so I think I will stop here now. This was, of course, so this greedy algorithm is part of your course. This perceptron learning algorithm, I wanted to explain you guys, but making. I mean, yeah, I don't know. I will not be asking you to prove this perceptual learning in your exam or something, of course. But we will see more stuff of this. So anyway, so we will meet again on Tuesday when we will discuss on the we'll go into some recursive algorithms and some dynamic programming algorithms. And before we kind of take a complete different direction of this for the algorithm, we have not done it in this class. So, by the way, I just wanted to ask you guys one more thing. Has the dean's office communicated with you anything about coming back to the campus?
Yes, sir. Yes, sir. So we received a message from the dean's office saying that offline classes may resume from 29th November. So if the teachers want, they can take offline classes.
Okay. And do you have any idea about how many people of you are thinking about coming back or something?
I guess. So I'm just guessing. 15-16 students should be able to come, I guess, in the class if offline classes starts.
Okay.
So yeah, so I also wanted to join. I'm not in the campus, but if the classes resume, then I will. Offline classes resume, then I will come back. Yes.
Okay. And has the dean told anything about the mixed end-sem exam?
No, sir, not yet.
Whether that will be compulsory offline?
Anyway, I guess it's expected to be offline.
Yes, sir.
Yeah.
Yes, sir. I mean, if like the things are developing for now,
yeah,
it's a great possibility that we have offline.
Yeah, so I'm actually very confused about what to do with it. So that's what I was asking, because.
So for now, the dean has allotted rooms and like.
Yeah, I know that they have allotted rooms, but
classrooms and they have said that it's not mandatory, but mixed mode classes can be, you can make arrangements for that.
Yeah, so that's the thing. I mean, I am personally not a big fan of mixed mode classes. I mean, I think many people are not. I mean, of course, we will prefer offline classes than online classes, but the mixed mode is the worst among them. And so I think what I will be doing is that I will continuing with the online classes, but I will keep an office hour or something like that, or some kind of discussion sessions other than the class hours, where I would be happy to meet whoever is there in campus personally or in person. So has the teachers told you anything about who is bringing what other than?
We have for sample surveys, we know that it is going to be purely online this semester.
And Professor Nuchiketa Chattopadhyay asked me personally whether how many students may come to his offline classes if he starts. I don't know. I mean, I have not communicated about this with my batchmates. But anyway, he has asked me some time ago that how many people may come.
Okay.
And Professor Anil Ghosh is already taking offline class. I mean, I should not say offline classes, but in
mixed mode.
So he comes to the campus. He takes the classes from a classroom.
So that he was
no. That I think many of us will be doing. Okay, many of us prefer taking from boards. Some of them are. I think even Anil, like, is he teaching in board or is he using that?
He's using a board.
Right?
Board.
So he's using the board. Okay.
And sir, some of us are going to his classes as well. I mean, physically.
Oh, some of you are already going to.
Yes, sir. Okay. But like from the previous class, I guess.
Okay. I mean, how was it actually? I mean, was it something you guys prefer?
I did not. I could not go to his first offline class, but I mean, I'm planning to go to.
Offline class will be good. I mean, the people who will be in the campus, they will be fine. But what happened to the people who are not in the campus? Okay, so they will be all listening from the online setting.
So there wasn't much of a difference. sorry.
There's not much of a difference.
So for the people who
No.
were attending the class online, we
Yeah.
couldn't really notice much of a difference from a totally offline class and a mixed mode class.
Okay. Okay, so good. So I will. Okay, let me think about it, and I will accordingly. I mean, I am going to the campus every day, but I'm just thinking about this class.
So I guess we also should discuss among ourselves and like who want to come in the offline class. We should first know among ourselves, I guess.
Yeah, that is also thing. And then I think there's some other issues. I mean, it's not very clear whether everybody can come in the class. I mean, they have been allowed. You guys have been allotted the room 700 or something. Now, if everybody comes back, it's not very clear whether the deans will allow all of you to come sit in the class.
Yes, that was before also. Like I think like some time back when it also was running in the mixed mode. If there were more number of students coming, they had to sit in some other rooms with their laptops, and then they had to do it that in online mode only, even though they are present there.
Yeah, something like that.
Yes.
Actually, 700 is a quite large room, so I don't think that problem will be there. Even if
700 is a quite large room.
yes, sir.
Okay. Okay, good. So I will just think about it, and I will anyway get back to you. Let's see how it evolves.
Okay, sir.
Sir?
Yeah.
So there is another thing you were talking about in the class group. Would it be preferable for you if we were to shift the tutorial class timings a bit further back on Friday itself, rather than having it at 7, if we could have it at something like 5? And
At
would it
5?
Right, because there wasn't any objection to it from anybody, and there are some people who are preferring that over having it this late. So would that be
I think
preferable to you?
it will be fine with me. Okay. So maybe it will be can you just send a mail to me, Manasvi, Omkar, and Sonlipa together,
Right.
and so that
Okay.
mostly they will be taking the classes. So if they are
Right.
fine with it, and you guys are preferring that, then it will be perfectly fine.
Okay. All right. Okay. Sir.
Okay. Okay. So see you on Tuesday.
Thank you, sir.
Thank you, sir.
Thank you, sir.